Shear stress.
A shear stress, denoted, is defined as the component of stress coplanar with a material cross-section. Shear stress arises from the force vector component parallel to the cross-section. Normal stress, on the other hand, arises from the force vector component perpendicular to the material cross-section on which it acts.
General shear stress.
The formula to calculate average shear stress is where.
Other forms of shear stress. Pure shear.
Pure shear stress is related to pure shear strain, denoted by the following equation. Where is the shear modulus of the material, given by. Here is Young's modulus and is Poisson's ratio.
Beam shear.
Beam shear is defined as the internal shear stress of a beam caused by shear force applied to the beam. Where. The beam shear formula is also known as Tsuravsky shear stress formula after Dmitry Ivanovich Tsuravsky, who derived it in 1855.
Semi-monocoque shear.
Shear stresses within a semi-monocoque structure may be calculated by idealizing the cross-section of the structure into a set of stringers, carrying only axial loads, and webs, carrying only shear flows. Dividing the shear flow by the thickness of a given portion of the semi-monocoque structure yields the shear stress. Thus, the maximum shear stress will occur either in the web of maximum shear flow or minimum thickness. Also, constructions in soil can fail due to shear. For example, the weight of an earth-filled dam or dike may cause the subsoil to collapse, like a small landslide.
Impact shear.
The maximum shear stress created in a solid round bar subject to impact is given as the equation. Where and
Shear stress in fluids.
any real fluids, liquids and gases included, moving along solid boundary will incur a shear stress on that boundary. The no-slip condition dictates that the speed of the fluid at the boundary, relative to the boundary, is zero, but at some height from the boundary the flow speed must equal that of the fluid. The region between these 2 points is aptly named the boundary layer. For all Newtonian fluids in laminar flow, the shear stress is proportional to the strain rate in the fluid, where the viscosity is the constant of proportionality. However, for non-Newtonian fluids, this is no longer the case, as for these fluids the viscosity is not constant. The shear stress is imparted onto the boundary as a result of this loss of velocity. The shear stress, for a Newtonian fluid, at a surface element parallel to a flat plate, at the point Y, is given by where. Specifically, the wall shear stress is defined as. In case of wind, the shear stress at the boundary is called wind stress.
Measurement by shear stress sensors. Diverging fringe shear stress sensor.
This relationship can be exploited to measure the wall shear stress. If a sensor could directly measure the gradient of the velocity profile at the wall, then multiplying by the dynamic viscosity would yield the shear stress. Such a sensor was demonstrated by AANAQWI and W.C. Reynolds. The interference pattern generated by sending a beam of light through two parallel slits forms a network of linearly diverging fringes that seem to originate from the plane of the two slits. See double-slit experiment. As a particle in a fluid passes through the fringes, a receiver detects the reflection of the fringe pattern. The signal can be processed, and knowing the fringe angle, the height and velocity of the particle can be extrapolated. The measured value of wall velocity gradient is independent of the fluid properties and as a result does not require calibration. Recent advancements in the micro-optic fabrication technologies have made it possible to use integrated diffractive optical element to fabricate diverging fringe shear stress sensors usable both in air and liquid.
Micropillar shear stress sensor.
A further technique is that of slender wall-mounted micropillars made of the flexible polymer PDMS, which bend in reaction to the applying drag forces in the vicinity of the wall. The sensor thereby belongs to the indirect measurement principles relying on the relationship between near wall velocity gradients and the local wall shear stress.